A common way that data can be represented is also through a scatter plot. Scatterplots display bivariate data as a set of points on the xy plane. Each axis represents a variable in the real-world scenario. Each point on the scatter plot represents a specific observation or a single data point. When we're looking at scatter plots, we often use lines of best fit or regression lines that describe the general trend based on all points in an algebraic equation format. So let's take a look at interpreting some scatter plots. This scatter plot shown in its line of best fit. What is the difference between the point M and the y value predicted? So any point that is on the line of best fit is going to be a prediction based on the trend, while all the actual points are true data points. And so here we have the data point M, which is represented by the ordered pair 15, 5. Now it's asking about the y value that would be predicted based by the line of best fit, which means that if we use the same x value, what is the y value that should have been predicted? And so we go up to our line of best fit, and we see what our y value is. Well, here our prediction shows a y value of 11 for the point 15, 11. So the difference between the two is the predicted y value less the given y value for the difference of 6. The scatter plot below shows relative housing cost and the population density for several large U.S. cities in the year 2005. The equation given represents the line of best fit. We want to identify the meaning of the different parts of the equation. So starting with 61, well, we need to think about what part of the linear equation is this value 61. Well, what's important about 61 is that it's its y-intercept. And when we look at the graph, we see the value 61 here, again on our y-intercept. So we have the ordered pair 0, 61. When describing the meaning of a point, just think about the associations in the units on the x and the y values and translate that into a sentence. So here we have the point 0, 61. So we think about, well, what does 0 mean? 0 in this context represents 0 per people per square mile. So when our population density is 0 people per square mile, then we're looking at, okay, what does the y value represent? Well, y is the percent of national average, the relative housing cost. So when our population density is at 0, the relative housing cost is 61% of the national average. So all we did to describe that value was look at what the ordered pair is and lay out what the x value represents and what the y value represents. Then we can look at the next part. What is the meaning of the 0.0125? And so we identify that, okay, well, this is the slope of our linear equation. Well, slope represents change in y divided by the change in x. So again, we need to do the same thing, but also look at it through the lens of change. As y changes, how does x change? Or as x changes, how does y change? So what we're looking at here is our slope is that it's written at a unit rate of 0.0125 divided by 1. Any number can be written as a unit rate by putting it under 1 if it's not already a fraction. And so here we have to think about the unit for our y values. Well, our y values again represent percent of national average, while our x value represents people per square mile. So the meaning here is that as the number of people per square mile increases, then we look at the y value. as the number of people per square mile increases by 1, the relative housing price increases by 0.0125% of the national average. So it's taking the x and y value meanings and attaching them to the numerical parts of these terms and these coefficients. We can also use this chart to answer a couple questions, which we'll do here. According to the graph predicted, relative housing cost for a population density of 15,000 people per square mile land is approximately what percent of the national average? So we look at 15,000 people per square mile and we want to find the predicted amount. So we look at 15,000 and we go up to our line of best fit, and 15,000 corresponds with the point 250 on the y-axis, which is 250% of the national average. That's our predicted amount. If we wanted a measured amount, we can see that there's also a city that has the same amount. And while it predicted to be 250,000, here we're looking at a percentage that's greater than 300% on the actual value. Next, according to the equation, the predicted relative housing cost for a population density of 5,000 people per square mile of land is what percent of the national average? So here what we're doing is we're actually looking at the equation and not necessarily the graph, but we can make a prediction. At 5,000, we know it's going to be somewhere in the range of 125%. Well, let's see what the actual value is when we plug it into our equation. So we take the equation y equals 0.0125, and we're going to multiply it by 5,000, and then we're going to add 61. And when we evaluate that, we get a solution that y equals 123.5%. So it's close to our estimate of 125, and so we get an exact value by using the equation. Now let's look at fitting a function to a scatter plot. So here we have two types of functions that we'll look at, linear functions as well as quadratic functions. Let's start with the linear. We're familiar with the form of the equation y equals mx plus b. When we're trying to sketch a line of best fit, we're just going to be approximating it. There are very formal ways to identify what a line of best fit is, most common being the least squares regression. But all we have to do is get an estimate, a close shot, and then we'll be looking at some multiple choice values and try and figure out which one makes the most sense. So what we're going to do is we're going to draw a line that goes through our graph. And we're just trying to get the line to go through the middle as best we can. We may even have to visualize the line. Okay, we might not be able to draw on it exactly, but we want to visualize it. And the first thing we want to do is we want to think about the slope. We want to identify the slope by checking the sign and then get a rough estimate for the slope. So here what I can do is take a couple points. Let's use a bright color here. Take a couple points on my line of regression and just kind of get it close. Doesn't have to be perfect. But I got a couple points here, and they're approximately the point 2100 and 150. And by using those points, now we can approximate our slope. And again, this is just going to be an estimate. So our slope will be the difference in y1 and y2 divided by the difference in x. So we get 50 over 10, or approximate slope of 5. And so we'll check our answer options and look for whatever slope has the most, is the closest to that. So we know our slope is approximately 5. Then we just have to estimate what our y-intercept is going to be. And so here we're just going to look closely and say, okay, well, if we follow this trend down, we know our y-intercept is going to be close to 0, and it's probably going to be negative. Now, because this continues off the graph, then we have to think about, well, what's our scale look like? And so we can kind of estimate here and see that this line is approximately going through the middle if I were to continue this scale mark down. And so it looks like our y-intercept is around negative 25. So B is approximately negative 25. So we can write our own little equation, our own little estimate, y equals 5x minus 25. And if we're dealing with a multiple choice question, we're just going to look for the one that matches the closest to our own estimate. The other type of linear regression that we'll have is a nonlinear regression for a quadratic. And here we're just looking for two main features. We're trying to identify what direction the parabola opens, whether it's up or down. If it opens up, then our a value is positive. If it opens down, our a value is negative. So when we look at this graph, we see how this is a nonlinear curve, and I can try to draw a curve here, and if I continue off the graph, I get this parabolic shape. And so we see that this parabola opens downward, which means we're going to have a negative leading coefficient. So we can ignore any answer options that have a positive leading coefficient. The next thing that we want to look at is the y-intercept, which, just like with a linear term, is the constant. So when we look at our little sketch here, we see that our y-intercept is approximately 300. So we look for the answer option that gives us the appropriate y-intercept.